This session will be Sarah Loos. She is completing her PhD at Carnegie Mellon University, and she is working on verification of hybrid systems under the supervision of Professor Andre Platzer, and she completed her practicum at Oak Ridge National Lab in 2013.
Michael, thank you very much for the introduction. Is the microphone working? Yes. Okay, great. Thank you so much for the introduction. So today I'll be talking to you about verifying distributed car and aircraft systems using logic and refinement. So what does that mean? Well, here, the question that we're always trying to answer in transportation is how can we move more people to more places faster? So on this slide, we can see a snapshot of air traffic over the US, and we get a little bit of a sense of what rush hour looks like in our skies and how crowded it can be up there. And on the right side of the slide, we see a little bit of a snapshot of what rush hour looks like on our roads, and every one of us has experienced that. Hopefully not, but maybe in our daily lives. So one thing that we can do to make these extremely large distributed systems with thousands of cars and thousands of aircraft more efficient is add computer controls to these systems. So we can add computer controls to the cars and allow them to follow a little bit closer to the car ahead. And we can use computer controls to aid the pilot and maybe let the pilot fly closer to other aircraft in the sky. Another benefit beyond efficiency is just in the safety of these systems. So if you have adaptive cruise control or emergency braking in your car, where your car is sensing the cars around you, you have things from that computer system that you can't get as a human driver. So the computer system has, for example, 360-degree vision because you can mount sensors all around the car and know exactly what's happening. You know, humans, we can only look in one direction. The computer system has faster reaction times than humans, and it won't fall asleep while it's driving on a long road trip. So you have a lot of benefits from adding these computer systems to your cars and computer controls in these physical real-world systems. However, we're adding software to these computer systems, and software is complicated. Software is easy to get wrong, especially when you're trying to get software to interface with the physical world. So we want to make sure that the software we use and the models that we use for these systems don't have mistakes, that we're not introducing bugs that could cause your car to crash when you're actually trying to avoid a collision. We don't want to be doing more harm than good by adding software to these systems. So the question that I try to address is how, once we decide to put these computer controls into these cars, making them cyber-physical systems, at what point, how can we make sure that that software is actually correct? Of course, you can build the car, you can build the aircraft, and then test it a bunch. But what if you find a bug at that point? What do? Well, you have to start over from scratch, build the aircraft again. It's very expensive to do things that way. Another thing that you can do is simulate a bunch of aircraft, or simulate all the cars in your system. And you can run this simulation 1,000,000 times, and you say, okay, well, I ran it 1,000,000 times. I probably got all the scenarios that'll actually come up on our highways, right? I'm not sure. How do I know that I have coverage if I've simulated it? Of course, these are both very useful methods. I would never suggest that car manufacturers skip these important steps. But we want something a little bit more of a stronger guarantee, something that gives us a strong guarantee that says, under all possible scenarios, under all possible circumstances, the model of our system shows that our software is not going to cause the aircraft to collide into each other or the cars to collide. We want to make sure we have something really strong. And to do that, we use formal verification techniques. So in the duration of my PhD, I've looked at several case studies. Here is the first one, where we have an arbitrary number of cars driving on the road. So this could be thousands and thousands of cars driving on a highway. And the cars can enter and exit the highway and change lanes and whatever else. And what makes this system difficult is that we have distributed dynamics. So one of the questions that we want to ask is we want to say, well, what happens with all these thousands of cars? Does one car make a decision here that causes a crash a mile down the road? Additionally, making this problem even harder is that the cars have only local sensors. So the cars don't get to know about the position and velocity of all the other cars on the highway, they only get to know about their closest neighbors. So we want to make sure that given local information, the cars can make a decision that has a safety property that's always true globally in the whole system. Another case study that we looked at was the distributed aircraft case. And this is very similar to the cars because we still have lots and lots of aircraft flying in the sky. But it's even more complicated because just like the cars, they move around, but they have even more complicated physical dynamics. So we have to use differential equations, just like with the cars, we use differential equations to represent the continuous dynamics of how these aircraft fly around. And in addition to the distributed dynamics, the continuous dynamics they have a lot of constraints. The aircraft have to keep a certain amount of speed so they don't stall. They can't stop, we can't ask them to turn on corners and things like that. So those are some of the things that make these distributed cyber-physical systems challenging to study. I've also studied several other case studies. All of these were modeled in something called differential dynamic logic, and then we verified the safety of these systems using a theorem prover called Chimera. So let's start with the distributed car control case. Let's start with just the basic case where we have two cars. So we want to design an emergency braking system or an adaptive cruise controller for this green car, so that whatever the red car does on the lane ahead of it, the green car is going to be sure to brake in time. So the green car is deciding, can I accelerate or can I brake? And of course, this is a continuous world, but our sensors are discrete. Our sensors are only going to tell us information about that red car at discrete points in time. Here's its position, here's its velocity. And then you have to wait a little while, and then you get an update again. So this green car has to make a decision, well, can I accelerate now, knowing that it may be driving blind for a little while until it gets that next update about the car ahead. So it has to be very careful not to accelerate unless it's certain that it can do so. So it has to be a little bit forward thinking. All right, so now let's add a little bit more complexity to this system. Suppose we have another car on another lane, and this car wants to change lanes into that middle lane. So one possible solution to this would be that this car might ask the green car to slow down and ask the red car to speed up to make a space so that it can move into the lane. This is a local maneuver. We could verify that this maneuver is safe locally for these three cars. But when we look at it globally, we can see that, oh, well, there might be another car farther up on the lane that's also trying to change into the same lane that we want. And now this red car is getting conflicting requests. He's being asked simultaneously to speed up and slow down. And this is an issue that we wouldn't have come across in the three-car case when we verified that. But it does come up in a global perspective of the system. So in our proof, we start with this basic building block of two cars. And we model these two cars, like I said, we use differential equations to model their continuous dynamics. And we use differential dynamic logic to model the software that will go on the cars to make those decisions on acceleration and braking. And we're able to verify this for two specific vehicles where that front vehicle is basically can do whatever it wants. And other researchers who've done formal verification have done similar things for two cars. They've done it for 3 cars, 4 cars, 6 cars, 14 cars. But they stopped there, and they don't look at the distributed system of cars. So what we do is we use this 2-car case as a base case, essentially, and then we quantify over a lane of cars. And we extend the 2-car case so that we can use that as a building block and piece it together with lots of other building blocks and allow for a verification of an entire lane of cars where you have n cars on the lane. And now we have a verification that's much stronger than just 2 cars or 14 cars. We have something that looks a little bit more global. From there, we build onto that, and we verify a system where we still only have 1 lane, but we have n cars on that lane, and those cars can enter and exit the lane. And then finally, we glue that block together with lots of other lanes, and now we have a system where cars can enter and exit the system and change lanes at will. And what we've provided is a formal verification that the controllers on these cars don't allow the cars to crash, no matter how long the cars are driving, and no matter what control choices they take. So if somebody slams on the brake at one point, then the whole system still stays safe. The next property that I'm going to talk about, the next system, is the distributed aircraft problem. So how can we design controllers for aircraft that make sure that the aircraft don't come too close to each other? So the story here is very similar to the story for cars. With aircraft, we still have local sensor limits. And here's a proposed collision avoidance maneuver for two aircraft that are on a collision path, where the two aircraft agree on a roundabout and then fly around the roundabout and continue on their way, and they've avoided a collision. And this property was actually proposed and verified safe and recently. It was actually proposed to replace a previously proposed maneuver that wasn't safe. So we want to have verification, because sometimes we think something's safe, but it's actually not. And this is great, but what happens when we have a third aircraft join the mix? Well, that's no problem. We can add another ring to our collision avoidance maneuver and have this third aircraft join the maneuver, and a fourth aircraft as well. And in fact, this specific maneuver was verified safe for up to 5 aircraft. But what happens when we try to prove it in the global case? So we try to extend this to be an arbitrary number of aircraft. And now there's another maneuver happening nearby that's already been happening that's outside of the sensor limits of those original aircraft. And so now we add aircraft to this maneuver and another aircraft, and we see that our maneuver that was supposed to avoid a collision has actually caused a collision. So now in that global case, we're not able to prove safety. We're not able to prove safe separation of the aircraft because we don't have it. So it's important to keep this in mind, this global perspective in mind when we're trying to verify things. So we looked at a different maneuver when we tried to prove the global case, and this maneuver was proposed by Palatino et al., where each aircraft is associated with a buffer disk, and it flies around with this buffer disk on one side of the aircraft. And when 2 buffer disks get within p distance of each other, then the aircraft start to go into a collision avoidance maneuver where they each circle around their own buffer disk until they're able to resolve the collision. Here, for example, we have aircraft I and aircraft J are flying sort of in the direction of each other, and their disks become too close, so they would have to enter a collision avoidance maneuver, and aircraft I would circle around its disk, and aircraft J would circle around its disk, and the closest they could get is that distance p, so the aircraft are still safely separated. Alternatively, aircraft J could send a message to aircraft I and say, look, can you flip your buffer disk to the other side of your aircraft? Aircraft I has an opening on the left side of its aircraft, so it could flip that buffer disk to the left side, and they could avoid doing the maneuver altogether and keep a little bit more efficiency in the system. So this property of trying to make sure that 2 aircraft are always separated can actually be broken down into 2 simpler properties that, taken together, will imply this. So we want these 2 aircraft to be separated. Well, we can show first that each aircraft stays on its buffer disk at all times, and second, that the disks are always staying separated from each other. So when we take these 2 properties together, we get the property that we're trying to prove. And what do we do in verification? Well, we want to prove that for all possible trajectories of this system, our safe separation property holds. And the way that we represent that in our logic is with a box modality. So we put a box around our model, and we say all possible trajectories of this model satisfy this safety property. And the first step of the proof is probably what you expect. We split it into these 2 simpler properties of the aircraft staying on their disks and the disks staying separated. And then the final step is something that we prove in our automated theorem prover, Chimera D. So this is something that we hand the model of the system and the property that we're trying to prove about it over to the computer. And then the computer uses Chimera D for distributed hybrid systems to prove that that safety property is always held by that model. And Chimera D works by splitting up the property into smaller and smaller pieces and doing this in parallel. So there are all these case studies that were previously out of scope for formal verification. They were previously too hard, especially these large distributed systems where we were only able to do it for a few cars or a few agents in the system. And now they are in scope, and there are a couple reasons for that. One reason is that we have improved the way that we do these methods. We've improved the methods for actually the algorithms that the computers use to break apart these systems and prove properties about them. And the other is that we just have more computation power. So automated theorem proving in the past has sometimes gotten a bad rap because it takes a lot of computation time. This is not an easy problem to solve. Down at the leaves, it's a doubly exponential problem, and the problem space generally is undecidable. So this is definitely a hard problem, but it's one worth solving. And with increased computation, we've actually found a lot of problems to be in scope that were out of scope before. So all of these problems were solved by researchers, researchers with PhDs in the field. But the question is, can we actually make these problems accessible to general industry people or to people who aren't experts in formal verification? And a quick answer is yes. So I co-created a course for undergraduates at Carnegie Mellon where we had undergraduates design controllers for these cyber-physical systems and model the systems with differential equations for the dynamics of the robots or cars or whatever they were modeling, and come up with safety properties for each of those systems. We allowed the students to turn in the models of their controllers first without a proof, and then we gave them back a simulation, so you can see here that some of them failed, and they didn't like that. So then the next iteration, they were required to turn in the model with a proof of correctness as well, and then they were able to pass the lab. So this is the very first lab. The second lab, the students, or the last lab of the class, the students are avoiding static obstacles. They're also avoiding dynamic obstacles. And these are all formally verified systems. So this was very impressive. We were really happy with the results that the students were able to come up with. And we also created a set of YouTube video tutorials for the course and for the tool so that the students could follow along. They could manipulate their assignments at the same time watching a tutorial video and being able to rewind and restart. So a little bit of a flip the classroom feel. So I have a conclusion slide, but I think I've run out of time. So I just want to express a great deal of thanks to CSGF and all the resources that they've provided. And thank you very much for all the wonderful conversations I've had with all of you over the last 4 years.